Hello there, and welcome to my channel. My name is Matthew Gray. I'm so glad you found your way here tonight, because we're about to drift through the vastness of space together, letting the quiet wonders of the cosmos guide us toward rest. Wherever you are right now, let this be your invitation to pause. Let the day's weight lift, the mental chatter fade, and your thoughts settle like stardust through an endless night. Tonight, we're venturing beyond our familiar sky into the universe itself. The cosmos is more harmonious, more perfectly balanced, and more gently arranged than we often realize. From galaxies that spin in ancient rhythms to stars that hum with invisible music. From nebulae that birth new worlds to the silent dance of planets across billions of years. The universe moves with a grace that will soothe you, surprise you, and remind you of something timeless. What you'll hear tonight reveals the hidden architecture of existence itself. Each fact is a doorway into understanding how everything, from the smallest particle to the largest galactic cluster, follows patterns so elegant they seem almost intentional. The universe isn't chaos. It's a grand design unfolding in slow motion, and we're part of that design. Some of what you discover may shift how you see the night sky. Other revelations might simply drift past like comets, beautiful and fleeting, leaving only a sense of peaceful wonder behind. If this journey brings you calm or stirs your curiosity, consider liking and subscribing. It helps others find their way here too, one restless mind at a time. But for now, let yourself sink into comfort. Take a slow, deep breath, and let's begin this gentle voyage through the quiet miracles of the universe. The universe is approximately 13.8 billion years old, and yet it still expands in every direction at once, stretching like a slow exhalation that never quite ends. Scientists measure this age through the faint afterglow of the Big Bang, a whisper of ancient light that still fills all of space. Called the cosmic microwave background, it's the oldest thing we can detect. It surrounds us completely, a warm echo from when the universe was just 380,000 years old, barely an infant in cosmic terms. At that early moment, space itself cooled enough for light to travel freely for the first time. Before then, the universe was so dense and hot that photons couldn't move without immediately colliding with particles. When those photons finally escaped, they began a journey that continues today, reaching our satellites and telescopes as faint radio waves. Background radiation, like it, is incredibly uniform, varying by only 1 part in 100,000 across the entire sky. That uniformity tells us something profound about the beginning of everything. The universe started smooth, almost perfectly smooth, with only the tiniest ripples that would eventually grow into galaxies and stars. And that smoothness, that gentle consistency, suggests an underlying order to creation itself. Ancient light like it connects us to a time before stars existed, before galaxies formed, when the universe was nothing but hydrogen, helium, and the promise of what was to come. Before the first stars ignited, the universe experienced what astronomers call the cosmic dark ages, a period lasting roughly 100 million years, when no light sources existed except that fading afterglow. Space was filled with neutral gas, simple atoms drifting in darkness, waiting. Temperatures dropped steadily as expansion continued, and gravity began its patient work, pulling atoms together in regions where those tiny early ripples had left slightly more matter than average. gathering clouds of hydrogen grew denser, slowly, incrementally, until the pressure at their cores became intense enough to spark fusion. When the first star finally lit up, it transformed everything. That initial ignition broke the cosmic silence, sending ultraviolet light streaming through the primordial gas, ionizing atoms and creating bubbles of cleared space. More stars followed, then more, each one contributing to a growing network of light that gradually filled the darkness. None resembled our Sun. They were massive, probably 100 to 200 times the mass of our Sun, burning incredibly hot and bright, but living only a few million years before exploding. Their deaths seeded space with heavier elements, carbon and oxygen and iron, materials that would eventually allow planets and life to form. Early stellar giants like them were the universe's first architects, building the elemental table from pure hydrogen and setting the stage for cosmic complexity. Creation of heavy elements continues today in the cores of massive stars, where fusion reactions proceed through predictable stages, each one building atoms layer by layer. A star begins by fusing hydrogen into helium, the process that powers our Sun and will continue doing so for another 5 billion years. When hydrogen runs low in the core, the star contracts slightly, heats up, and begins fusing helium into carbon. It happens gradually, without drama, just a natural progression as gravitational pressure seeks equilibrium with outward radiation. In more massive stars, the process continues further. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each stage produces less energy than the last, and each stage lasts for a shorter time. A massive star might spend millions of years burning hydrogen, but only days burning silicon. Iron represents the end of the line, because fusing iron consumes energy rather than releasing it. When a massive star's core becomes iron, fusion stops, support vanishes, and the core collapses in less than a second. Rebound from that collapse creates a supernova, an explosion so powerful it briefly outshines an entire galaxy. That explosion scatters newly formed elements across light years of space, mixing them with the interstellar medium. Scattered elements drift through space until gravity gathers them again, incorporating them into new stars, new planets, new possibilities for structure and life. Our own solar system formed from such enriched material about 4.6 billion years ago, when a cloud of gas and dust began collapsing under its own gravity. A shockwave from a nearby supernova probably triggered the cloud's collapse, the same kind of explosion that had previously created many of the atoms within it. As it collapsed, it spun faster, flattening into a disk with a dense center where the Sun would form. Temperature at the center rose until nuclear fusion ignited, and the Sun began its long, steady burn. Meanwhile, in the disk surrounding the young Sun, dust grains stuck together through static electricity and gentle collisions. Grains formed larger clumps, which formed larger ones still, eventually creating objects, kilometers across, called planetesimals. Planetesimals collided and merged, building the planets over tens of millions of years. Inner regions, close to the Sun's heat, lost most of their lighter elements, like hydrogen and helium, leaving behind rocky planets made of heavier materials. Outer reaches remained cold enough for ice to persist, allowing the giant planets to capture enormous atmospheres of hydrogen and helium. Simple physics governed the entire process, gravity and momentum, following their natural courses, organizing chaos into structure. Identical processes have occurred around countless other stars, creating solar systems throughout the galaxy, each one a variation on the same fundamental theme. Between 200 billion and 400 billion stars fill the Milky Way galaxy, each one potentially surrounded by planets, and the galaxy itself is just one of perhaps 2 trillion galaxies in the observable universe. When we look up at the night sky, we see perhaps a few thousand stars with our naked eyes, all of them neighbours in our small corner of the galaxy. Stretching about 100,000 light-years across, the Milky Way is a flat disk with spiral arms curving through it like a slowly turning pinwheel. Our solar system sits about 26,000 light-years from the galactic centre, orbiting around it at a speed of roughly 500,000 miles per hour. Despite that enormous velocity, completing one orbit takes about 230 million years. Last time Earth was in exactly our position relative to the galactic centre, dinosaurs had just begun to appear. Rotation isn't like a solid disk, though. Stars closer to the centre orbit faster than stars farther out. And the spiral arms themselves aren't fixed structures, but density waves that pass through the distribution of stars. As stars move through denser regions, their gravity compresses the interstellar gas, triggering new star formation. Cycles of birth and death, like these, give the galaxy its structure, maintaining those elegant spiral arms through billions of years of slow rotation. Most galaxies contain a supermassive black hole at their center, an object so dense that nothing, not even light, can escape once it crosses the event horizon. At the center of our galaxy sits Sagittarius A, containing about 4 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. Despite that incredible mass, it's relatively quiet right now, consuming only small amounts of material and producing modest radiation. We know it's there because we can track stars orbiting around it, some completing their loops in just a few years, despite travelling at speeds approaching 3% of light speed. Orbits follow precise elliptical paths, proving that something with enormous mass sits at that central point, even though we can't see it directly. When matter falls toward a black hole, it forms an accretion disk, a swirling band of superheated gas that glows intensely before crossing the event horizon. Friction within such a disk converts gravitational potential energy into heat and light, making active black holes some of the brightest objects in the universe. Our galactic center's black hole may have been much more active in the past, possibly explaining mysterious bubbles of gamma radiation that extend above and below the galactic plane, remnants of ancient outbursts. Massive objects like them, once considered exotic theoretical possibilities, now appear to be fundamental components of galaxy formation, helping to regulate starbirth across cosmic time. Black holes don't actually pull harder than any other object of the same mass. They simply allow matter to get much closer to the center of mass before encountering a surface. If you could somehow replace the Sun with a black hole of equal mass, Earth's orbit wouldn't change at all. We'd lose light and heat, certainly, but gravitationally, nothing would be different from our current situation. Peculiar nature of black holes comes from what happens near the event horizon, the boundary beyond which escape becomes impossible. At that boundary, space itself is falling inward at the speed of light. Anything inside, even light beams trying to travel outward, gets swept along with that falling space, like someone trying to swim up a waterfall, moving faster than they can possibly swim. Time also behaves strangely near black holes. As you approach the event horizon, time slows relative to distant observers. If you were to watch someone fall into a black hole, you'd see them slow down as they approached, their image freezing at the horizon, redshifted into invisibility, but never quite crossing from your perspective. Meanwhile, the falling person would cross through in finite time by their own clock, experiencing nothing special at the horizon itself, only realizing too late that they could no longer turn back. Strange relationships between space, time, and gravity reveal themselves most extremely around black holes, but affect everything everywhere, just more subtly. Time itself moves at different rates depending on how deep you are in a gravitational field, an effect that's both measurable and essential to modern technology. GPS satellites orbiting Earth experience time slightly faster than clocks on the surface because they're higher in Earth's gravitational field. Difference is tiny, only about 38 microseconds per day, but it accumulates quickly. If GPS systems didn't account for time dilation like it, navigation errors would grow by about 6 miles every single day. Systems work by comparing signals from multiple satellites, calculating position based on the travel time of radio waves. Calculations require incredibly precise timing, and that precision is only possible because engineers programmed the satellites to adjust for relativistic effects. It isn't just abstract physics, it's practical technology that most people use without realizing the underlying complexity. Same effect occurs everywhere. A clock at sea level runs slightly slower than a clock on a mountaintop. Difference is far too small for human senses to detect, but atomic clocks can measure it easily. Time is not a fixed, universal river flowing at the same rate everywhere. It's more like a landscape, with hills and valleys, flowing faster in some places and slower in others. Gravity shapes not just the paths that objects follow through space, but also the rate at which they experience time itself. Speed of light in vacuum is exactly 299,792,458 meters per second, and remains the same regardless of how fast you're moving when you measure it. Constancy seems impossible at first. If you're on a train moving forward at 50 miles per hour, and you throw a ball forward at 20 miles per hour, someone standing beside the tracks sees the ball moving at 70 miles per hour. Velocities add together in our everyday experience. But light doesn't follow such patterns. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, you see the light leaving at its normal speed. Someone watching from a planet also sees that light moving at its normal speed, not at 1.5 times light speed. Our universe preserves the constancy of light speed by adjusting space and time instead. As objects move faster, they experience length contraction and time dilation, effects that exactly compensate to keep light speed constant from all perspectives. Strange behavior isn't just a property of light, it's actually a property of space-time itself. Light just happens to reveal it because photons always travel at such a fundamental speed limit. What the constancy of light speed tells us is something deep about the structure of reality, suggesting that space and time are more flexible than our intuitions assume. Nothing with mass can reach the speed of light, because doing so would require infinite energy. But the universe itself has no such restriction and can expand faster than light. Galaxies we see today are moving away from us, and the most distant ones are receding faster than light speed because the space between us and them is expanding. It doesn't violate relativity because the galaxies aren't moving through space faster than light. They're being carried along as space itself stretches. Think of dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, but they're not actually traveling across the rubber surface. Surface itself is expanding, carrying them along. In the same way, galaxies maintain their position in their local space, while distances between them grow. Expansion was discovered in the 1920s, when Edwin Hubble noticed that distant galaxies showed redshifted light, meaning their light waves were stretched to longer, redder wavelengths. Farther away a galaxy was, the more its light was redshifted, suggesting that distance and recession speed were proportional. Relationship, now called Hubble's law, implies that the universe was once much smaller and denser, leading to the Big Bang Theory. Expansion continues today, and recent measurements show it's even accelerating, driven by something we call dark energy that seems to push space apart. Dark energy makes up about 68% of the universe's total energy content. Yet, we have no direct evidence for it, except through its gravitational effects on cosmic expansion. When astronomers measured distant supernovae in the late 1990s, they expected to find that the universe's expansion was slowing down due to gravity pulling everything together. Instead, they discovered the opposite. Expansion was speeding up, as if something was pushing against gravity's attractive pull. They named the mysterious influence dark energy, though the name doesn't explain anything about its nature. Simplest explanation is that empty space itself has energy, a property Einstein included in his equations as the cosmological constant. He later called it his biggest blunder after expansion was discovered, thinking a static universe would have been more elegant. But it turns out his cosmological constant may have been correct after all, just with a very small value that only becomes important over cosmic scales. If space has intrinsic energy, then as the universe expands and creates more space, it also creates more of such energy, which drives further expansion in a feedback loop. Acceleration, like it means the universe will continue expanding forever, growing colder and more dilute, eventually reaching a state where galaxies outside our local group disappear beyond the horizon of observability. Observable universe has a definite edge, not because space ends there, but because light from beyond that distance hasn't had time to reach us yet. At 13.8 billion years old, the observable universe is actually about 93 billion light-years across, not 27.6 billion, as you might expect from doubling the age. Discrepancy exists because of cosmic expansion. Light that was emitted from distant regions when they were much closer to us has been traveling toward us for billions of years. But during that time, the space between us and those regions has been expanding, stretching the journey. Most distant light we can see was emitted about 13.8 billion years ago, but the region that emitted it is now about 46 billion light-years away due to all that expansion. It creates a horizon, a cosmic edge beyond which events can't yet affect us because their light hasn't arrived. Every day, as time passes, such a horizon expands, and we can see slightly farther, though the acceleration of expansion means that galaxies beyond a certain distance will never become visible, no matter how long we wait, because they're receding faster than their light can approach us. What appears as an edge of the observable universe is not a wall or a boundary in space, but rather a limitation imposed by the finite age of the universe and the finite speed of light. Looking out into space is the same as looking back in time, since light takes time to travel, meaning telescopes are actually time machines that show us the universe as it was, not as it is. When you look at the moon, you see it as it was about 1.3 seconds ago, the time it takes light to cross that distance. Our sun appears as it was 8 minutes ago. Alpha Centauri, the nearest star system, appears as it was 4.3 years ago. When astronomers observe distant galaxies, they're seeing ancient history. A galaxy 10 billion light-years away appears to us as it existed 10 billion years ago, when the universe was less than 4 billion years old. We see that galaxy in its youth, probably looking very different from how it appears today. Time delay effect means we can study cosmic evolution directly by comparing nearby galaxies to distant ones. Nearby galaxies show us the present, while progressively more distant galaxies show us earlier and earlier epochs. Most distant galaxies we've detected are visible as they were just a few 100 million years after the Big Bang, appearing as small, irregular collections of stars very different from the mature spiral and elliptical galaxies we see nearby. Such a unique property of light allows astronomers to reconstruct the history of the universe, watching it grow and change from a simple beginning into the complex web of galaxies we see today. Cosmic Web describes how matter is distributed throughout the universe, with galaxies clustered along filaments that surround vast empty voids, creating a structure that resembles neurons in a brain or the scaffolding of a sponge. Computer simulations of cosmic evolution consistently produce such web-like patterns when started with conditions matching the early universe. Gravity amplifies the tiny density variations present after the Big Bang, pulling matter into denser regions while evacuating the spaces between them. Over billions of years, the process creates filaments hundreds of millions of light-years long, where galaxies form and cluster, separated by voids that contain almost nothing. Largest structures in the universe follow such patterns, with superclusters of galaxies forming at the intersections of multiple filaments. Our own local group of galaxies, which includes the Milky Way and Andromeda, sits on one of those filaments, part of the larger Virgo supercluster, which itself is part of an even larger structure called Laniakea. Structures emerged naturally from the action of gravity on matter, requiring no special organization or planning. Same forces that make an apple fall also shape the distribution of galaxies across the universe, operating on incomparably different scales, but following identical mathematical laws. Web-like organization reveals itself in galaxy surveys, showing that structure exists at every scale, from individual galaxies to the largest features we can measure. Gravity is the weakest of the four fundamental forces by an enormous margin, and yet it dominates the universe at large scales because it only attracts, never repels, and because it acts on all matter regardless of type. Electromagnetic force, which holds atoms together and creates chemistry, is about 1 billion times stronger than gravity. Yet, a small magnet can overcome Earth's entire gravitational pull when picking up a paperclip. Strong nuclear force, which binds atomic nuclei together, is even more powerful, though it only operates over distances smaller than an atomic nucleus. Weak nuclear force governs certain types of radioactive decay and plays a role in how the sun produces energy. Despite being the weakest, gravity accumulated matter into stars, galaxies, and galaxy clusters over billions of years because it adds up without cancelling out. Positive and negative electric charges can cancel, leaving objects electrically neutral, but mass and energy only produce attractive gravity. Every particle, every photon, every bit of energy contributes to the gravitational field, and the effect accumulates across cosmic distances. Patient accumulation allows gravity to sculpt the large-scale structure of the universe. Relative weakness of gravity compared to other forces is actually quite fortunate for life, because if gravity were much stronger, stars would burn much faster, and planets would have difficulty maintaining stable orbits. Stars follow predictable life cycles, determined almost entirely by their mass, spending most of their existence in a stable phase called the main sequence, where they fuse hydrogen into helium in their cores. Our Sun is about halfway through its main sequence lifetime, having burned steadily for about 4.6 billion years, and expected to continue for another 5 billion. More massive stars burn through their fuel much faster, sometimes lasting only a few million years, while stars with less mass than our Sun can burn for trillions of years, far longer than the current age of the universe. Relationship between mass and lifetime seems counterintuitive at first. Massive stars have more fuel, so shouldn't they last longer? But they also burn that fuel at dramatically higher rates because their greater mass creates stronger gravitational compression in the core, driving faster fusion reactions. A star with 10 times the Sun's mass might last only 20 million years. A star with half the Sun's mass could last 80 billion years or more. Smallest stars, called red dwarfs, barely massive enough for fusion to occur, burn so slowly and efficiently that not a single red dwarf has yet reached the end of its main sequence lifetime since the universe began. Tiny stars like them represent the universe's future, the last lights that will burn long after all larger stars have exhausted their fuel and faded. When the Sun eventually exhausts its core hydrogen, it will swell into a red giant, expanding to perhaps 100 times its current diameter, possibly engulfing Mercury and Venus, and certainly making Earth uninhabitable. It won't happen suddenly, but gradually, over hundreds of millions of years, as the core contracts and heats up, causing the outer layers to expand and cool. Our Sun will spend about 1 billion years as a red giant, fusing helium in its core and hydrogen in a shell around it. During such a phase, it will lose much of its outer material through a stellar wind, gentle streams of particles flowing outward into space. Eventually, the core fusion will cease when helium is exhausted, and without the outward pressure from fusion, gravity will compress the core into a dense sphere about the size of Earth, called a white dwarf. Outer layers will drift away as a planetary nebula, a glowing shell of gas illuminated by ultraviolet light from the exposed hot core. Planetary nebulae have nothing to do with planets. They were named by early astronomers who thought they looked similar to planets through small telescopes. White dwarf core will remain, no longer producing energy through fusion, but still hot from the compression, slowly radiating away its heat over trillions of years. Transformation of the Sun into a red giant marks the end of Earth as a habitable world. but the process unfolds so slowly that it poses no concern for countless generations. White dwarfs are incredibly dense, with a mass comparable to the Sun compressed into a sphere the size of Earth, meaning a teaspoon of white dwarf material would weigh about 15 tons. Extreme density occurs because white dwarfs are supported against further collapse not by heat or fusion, but by quantum mechanical pressure from electrons. In normal matter, electrons occupy various energy levels around atomic nuclei. But in a white dwarf, the atoms are crushed so close together that electrons are stripped away and packed extremely tightly. A quantum principle called the Pauli exclusion principle prevents two electrons from occupying the same quantum state, and it creates a pressure that resists compression. As long as the white dwarf's mass stays below about 1.4 solar masses, electron degeneracy pressure can support it indefinitely. Above that limit, called the Chandrasekhar limit, the pressure isn't enough, and the white dwarf will collapse further. Surface of a white dwarf is extraordinarily smooth because gravity is so strong there that any irregularity would quickly be pulled down. Surface gravity on a white dwarf is about 100,000 times Earth's gravity, meaning you would weigh about 100,000 times more there, though you'd be crushed long before that became relevant. Stellar remnants like them cool slowly, eventually becoming black dwarfs after trillions of years, cold dark spheres of degenerate matter floating through space. If a white dwarf has a companion star and pulls matter from it, the accumulated material can trigger a thermonuclear explosion called a nova, temporarily brightening the white dwarf by a factor of thousands or even millions. Stolen material, mostly hydrogen from the companion's outer layers, builds up on the white dwarf's surface, compressed by intense gravity and heated by the white dwarf's residual heat. Eventually, conditions become right for sudden fusion, and the accumulated hydrogen ignites in a runaway reaction. Unlike the controlled fusion in a star's core, ignition happens all at once across the surface, producing an enormous burst of energy. Explosion blows away the accumulated material, and the system returns to normal, potentially repeating the process if matter transfer continues. In some cases, enough material accumulates to push the white dwarf over the Chandrasekhar limit, triggering a different and much more violent type of explosion, called a Type Ia supernova. In such a scenario, the entire white dwarf is destroyed, converting a significant fraction of its mass into energy in a fraction of a second. Type Ia supernovae are so consistent in their brightness that astronomers use them as standard candles to measure cosmic distances. Reliability of Type Ia supernovae made them vital to discovering dark energy, since observations of distant supernovae revealed that cosmic expansion is accelerating. Neutron stars form when a star more massive than about 8 solar masses runs out of fuel and its core collapses. But not quite enough mass remains to form a black hole. Collapse is catastrophic. In less than a second, a core roughly the size of Earth compresses down to a sphere about 12 miles across. Electrons are forced into protons, converting them into neutrons and releasing a burst of neutrinos. Result is an object so dense that a teaspoon of neutron star material would weigh about 4 billion tons, equivalent to the entire human population, compressed into a sugar cube. Neutron stars are supported by neutron degeneracy pressure, similar to how electron degeneracy supports white dwarfs, but capable of withstanding much stronger gravity. surface of a neutron star is extraordinarily strange. Gravity there is about 100 billion times Earth's gravity, strong enough that light is noticeably bent by the gravitational field. Crust is thought to be crystalline, a lattice of iron nuclei, but compressed into configurations impossible on Earth. Deeper layers consist of increasingly exotic matter, possibly including exotic particles and states of matter that can't exist anywhere else in the observable universe. Objects like them represent matter at its absolute densest stable state, just barely avoiding complete gravitational collapse into a black hole. Many neutron stars spin at incredible rates, sometimes hundreds of times per second, because as a star's core collapses, conservation of angular momentum causes it to spin faster. The same principle that causes a figure skater to spin faster when pulling their arms inward. Before collapse, the core might have taken weeks to complete one rotation. After collapse, that same rotation rate is compressed into an object millions of times smaller in diameter, and the rotation rate increases proportionally. Fastest known pulsar spins 716 times per second, meaning a point on its equator is moving at about 1/4 the speed of light. Rapidly spinning neutron stars often emit beams of radiation from their magnetic poles. As the star rotates, the beams sweep across space like lighthouse beams. If Earth happens to lie in the path of such beams, we detect regular pulses of radio waves, X-rays, or even visible light, which is why objects like them are called pulsars. Pulses are extraordinarily regular, more precise than most atomic clocks. In fact, when pulsars were first discovered in the 1960s, astronomers briefly considered whether they might be signals from alien civilizations, since no natural process was known that could produce such regular pulses. Discovery that pulsars were actually rotating neutron stars solved the mystery and confirmed predictions about extreme stellar remnants like them. Magnetic fields of neutron stars are the strongest known in the universe, typically about 1 trillion times stronger than Earth's magnetic field. And some neutron stars, called magnetars, have fields even more powerful. Fields are so intense, they affect the very structure of space itself. Atoms near a magnetar's surface would be stretched into elongated shapes, and the vacuum itself would exhibit strange optical properties, behaving differently for light polarized in different directions. If you were somehow able to get within about 1,000 miles of a magnetar, its magnetic field would be strong enough to disrupt the molecular bonds in your body, though you'd have numerous other problems to deal with first, including lethal radiation and tidal forces that would tear you apart. Energy stored in magnetic fields gradually leaks away over thousands of years, occasionally causing the neutron star's crust to crack and shift, releasing tremendous bursts of energy. Starquakes can produce gamma-ray bursts bright enough to detect from across the galaxy. Combination of extreme density, rapid rotation, and intense magnetic fields makes neutron stars among the most extreme environments in the universe. Despite extremes like them, neutron stars follow the same physical laws as everything else, demonstrating that those laws remain valid even under conditions utterly unlike anything we experience on Earth. When two neutron stars orbit each other closely, they emit gravitational waves, ripples in space-time itself, that carry energy away from the system. As energy is lost, the orbit gradually shrinks, causing the neutron stars to spiral slowly inward toward each other. Process can take billions of years, but the final moments are spectacular. As the neutron stars approach, the orbital period decreases from years to days, to hours, to seconds, and the amplitude of gravitational waves increases. In the last fraction of a second before merger, the two neutron stars are orbiting each other hundreds of times per second, generating gravitational waves strong enough to noticeably stretch and squeeze space itself, even at cosmic distances. When they finally collide, the merger produces several things. First, a burst of gravitational waves that propagates outward at light speed, detected by instruments like LIGO that can measure distortions smaller than the diameter of a proton. Second, a flash of light across the electromagnetic spectrum, from radio waves to gamma rays. Third, a spray of heavy elements created by rapid neutron capture, including gold, platinum, and uranium. Called RR process nucleosynthesis, it's probably the main source of elements like them in the universe. Collision either forms a heavier neutron star, or, if the combined mass exceeds the limit for neutron degeneracy pressure, collapses directly into a black hole. Gravitational waves were first detected directly in September 2015, confirming a major prediction of Einstein's general relativity made 100 years earlier. Detected waves came from two black holes merging about 1.3 billion light-years away. Each black hole had a mass about 30 times that of the Sun, and they spiraled into each other over millions of years before finally colliding. Merger itself lasted only a fraction of a second, but in that brief time, it released more energy than all the stars in the observable universe were producing combined, though almost entirely in the form of gravitational waves rather than light. Waves stretched and squeezed space as they passed Earth, but only by an incredibly tiny amount. LIGO detectors consist of two 4-kilometer-long tunnels arranged in an L shape, with laser beams bouncing back and forth to measure the distance between mirrors at each end. When the gravitational wave passed, it changed distances by about 1/10,000th the diameter of a proton. Yet, the instruments were sensitive enough to detect such a change. Since that first detection, dozens more have been observed from various combinations of black holes and neutron stars colliding. Observations like them opened a completely new way of studying the universe, allowing us to detect events that produce little or no light, and confirming that massive objects really do curve space-time the way Einstein's equations predict. Collision of neutron stars or black holes produces jets of matter and energy moving at nearly the speed of light, creating what astronomers call gamma-ray bursts, the most luminous electromagnetic events known. For a few seconds, a gamma-ray burst can shine with the luminosity of the entire rest of the universe combined. Bursts occur somewhere in the observable universe about once per day, always in distant galaxies, each one marking the catastrophic end of a massive star or the collision of compact objects. If a gamma-ray burst occurred in our galaxy and its jet pointed toward Earth, it could damage the ozone layer and potentially cause a mass extinction, but the probability of such happening is extremely low. Most gamma-ray bursts occur billions of light-years away, and their jets are tightly focused beams covering only a small fraction of the sky. Focusing means we only detect bursts when Earth happens to lie in the path of the jet, suggesting that many more occur that we simply don't see. Energy comes from matter falling into the newly formed black hole, with some of it being channeled along the rotation axis and accelerated to extreme speeds. Brief duration of events like them means astronomers must rapidly redirect telescopes to catch the fading afterglow, a challenging observational problem that requires automated systems and international cooperation. Despite their incredible violence, the universe remains remarkably stable and predictable on average, with local catastrophes having little effect on the overall cosmic environment. Space between stars is so vast that even in a galaxy containing hundreds of billions of stars, stellar collisions almost never happen. When two galaxies merge, as the Milky Way and Andromeda will in about 4 billion years, the stars themselves pass by each other like two clouds of gnats interpenetrating. Probability of any two stars actually colliding during a galactic merger is negligibly small. What does interact is the gas between stars, which can trigger enormous bursts of new star formation. Gravitational influence of the merging galaxies disrupts the gas clouds, compressing them and initiating the collapse that forms new stars. Starburst. Galaxies can produce stars hundreds of times faster than the Milky Way currently does. Eventually, the two galaxies settle into a new equilibrium, usually forming an elliptical galaxy rather than preserving the spiral structure. Our future merger with Andromeda will transform the Milky Way into a larger elliptical galaxy, though such a process will take several billion years to complete. Merger poses no danger to individual star systems, including our own, since the vast distances between stars ensure they remain isolated even during cosmic collisions like them. Andromeda Galaxy is approaching us at about 70 miles per second, but it's also moving sideways relative to us. So instead of a head-on collision, the merger will be more of a complicated dance lasting several billion years. Both galaxies will pass through each other, their mutual gravity distorting their shapes and slinging stars into long tidal tails. They'll separate briefly, slow down, reverse direction, and approach again, possibly passing through each other multiple times before finally settling. During passages, the Sun and Earth will likely be flung out of their current orbit, perhaps ending up in a different part of the merged galaxy entirely. There's even a small chance we could be ejected completely, becoming part of the intergalactic void. None of it matters much for life on Earth in the short term, since the Sun's evolution into a red giant will occur before the merger is complete, rendering Earth uninhabitable long before any effects from the collision become relevant. Merger is inevitable because the Milky Way and Andromeda are the two dominant galaxies in our local group, and their mutual gravitational attraction will eventually overcome the expansion of space between them. Slow motion collision like it represents the kind of gravitational interaction that shaped galaxies throughout cosmic history, with smaller galaxies merging to form larger ones over billions of years. Galaxies grow through mergers, but they also grow by accreting smaller satellite galaxies over time. Dozens of satellite galaxies orbit the Milky Way, some containing only a few thousand stars, slowly being torn apart by tidal forces. Sagittarius dwarf elliptical galaxy is currently in the process of being absorbed, stretched into a long stream of stars that wraps multiple times around the Milky Way. Over the next few 100 million years, it will be completely incorporated, its stars mixing with the existing population. Process has happened many times in the past, and forensic analysis of stellar populations reveals evidence of numerous past mergers. Some globular clusters, dense spherical collections of old stars that orbit the Milky Way, are probably the cause of dwarf galaxies that were stripped of their outer stars during assimilation. Milky Way's disk shows warps and ripples that are likely caused by the gravitational influence of ongoing mergers. Even the Sun itself might have formed in a different galaxy that was later absorbed, though there's no way to know for certain. Hierarchical assembly like it, small structures merging to form larger ones, characterizes how galaxies form and evolve over cosmic time. Oldest stars in the Milky Way are found in its halo and globular clusters, with ages approaching 13 billion years, meaning they formed when the universe was less than 1 billion years old. Stars like them are chemically different from younger stars like the Sun, containing far fewer heavy elements because they formed before many cycles of stellar death and enrichment had occurred. Astronomers classify stars by their metallicity, using the term metal to describe anything heavier than helium, even though elements like carbon and oxygen aren't metals in the chemical sense. Oldest stars are metal poor, sometimes containing less than 1,000th the heavy element abundance of the Sun. Ancient stars are typically small red dwarfs, since more massive stars would have already exhausted their fuel and died. Studying them provides clues about conditions in the early universe and the chemical evolution of galaxies. Finding extremely metal-poor stars is one of the goals of modern stellar astronomy, since rare objects preserve information about the earliest generations of star formation. Each new discovery of an extremely old, metal-poor star adds another piece to the puzzle of how the universe transitioned from simple hydrogen and helium to the complex chemical diversity we observe today. Our Sun itself is about 4.6 billion years old, a middle-aged star already halfway through its main sequence lifetime. It formed from a cloud of gas and dust that had been enriched by multiple previous generations of stars, giving it a relatively high metallicity compared to older stars. Every atom heavier than helium in your body, including the carbon in your DNA, the oxygen you breathe, and the iron in your blood, was created inside a star that died before the Sun formed. Atoms were scattered into space, mixed with primordial hydrogen and helium, and eventually incorporated into the cloud that became our solar system. You are literally made of stardust, not as a poetic metaphor, but as a literal description of your atomic composition. Phrase was popularized by Carl Sagan, though the concept had been understood by astronomers for decades before he made it widely known. Nuclear fusion reactions inside stars are the only known processes that can create heavy elements in significant quantities, aside from the Big Bang itself, which only produced hydrogen, helium, and trace amounts of lithium. Our Sun will eventually return many atoms to space when it becomes a red giant and sheds its outer layers, allowing them to become part of future generations of stars and planets. Planets in our solar system all orbit in roughly the same plane because they formed from a flattened disk of material around the young Sun, a consequence of angular momentum conservation during the cloud's collapse. That disk, called the protoplanetary disk, contained dust grains, ice particles, and gas, all orbiting in the same direction. Collisions between particles tended to average out random motions, leaving only the rotation that was consistent with the overall spin of the system. Over time, particles in the disk stuck together, forming larger and larger objects through a process called accretion. Near the Sun, high temperatures meant only rocky materials and metals could remain solid, creating the terrestrial planets. Farther out, beyond what's called the frost line, temperatures were low enough for water ice and other volatile compounds to remain frozen, allowing the formation of much larger cores that could capture substantial atmospheres of hydrogen and helium from the surrounding nebula. It's why the outer planets are gas giants, while the inner planets are rocky. Asteroid belt between Mars and Jupiter represents material that never coalesced into a planet, probably due to Jupiter's gravitational influence, preventing the formation of a planetary embryo. Orderly arrangement of the solar system reflects its origin from a rotating disk, with the same processes likely occurring around most young stars throughout the galaxy. Jupiter contains more mass than all the other planets combined, about 318 times Earth's mass. Yet, it's still only 1,000th the mass of the Sun. Composition is similar to the Sun's, mostly hydrogen and helium, but it never accumulated enough mass for fusion to ignite in its core. If Jupiter were about 80 times more massive, it would qualify as a brown dwarf, capable of fusing deuterium. And if it were about 13 times more massive than that, it would be a true star fusing ordinary hydrogen. Instead, Jupiter remains a planet, though a very large one. Interior is under such extreme pressure that hydrogen transitions into a metallic liquid state, conducting electricity and generating the planet's powerful magnetic field. Field is about 20,000 times stronger than Earth's and creates enormous radiation belts that would be lethal to unshielded spacecraft. Jupiter's rapid rotation, completing one turn in less than 10 hours despite its size, combines with convection in the interior to drive powerful weather systems. Great Red Spot, a storm larger than Earth that's been raging for at least 350 years, is the most famous example. Massive size has profoundly influenced the development of the solar system, both through its gravitational sculpting of asteroid orbits and through its role in possibly migrating inward and outward early in solar system history. Saturn's rings are the most spectacular planetary feature in the solar system, composed of countless chunks of ice and rock, ranging from grain-sized particles to house-sized boulders, all orbiting in a disk less than 100 meters thick in most places, but extending more than 175,000 miles from the planet. Despite their impressive appearance, the total mass of the rings is relatively small, perhaps equivalent to one of Saturn's small moons. Rings are probably not primordial features left over from the solar system's formation, since their bright, relatively pristine appearance suggests they're at most a few 100 million years old. They may have formed from a moon that wandered too close to Saturn and was torn apart by tidal forces, or from a collision between moons. Roche limit defines the distance inside which tidal forces overcome a moon's self-gravity, preventing material from coalescing. Saturn's rings lie inside such a limit, which is why they remain as a flat disk of particles, rather than gathering into larger moons. Rings show intricate structure with thousands of individual ringlets, gaps, and density waves, much of structure maintained by gravitational interactions with Saturn's many moons. Some moons orbit within the rings themselves, called shepherd moons, whose gravity helps confine material and create sharp edges to certain rings. Titan, Saturn's largest moon, is is the only moon in the solar system with a substantial atmosphere, thicker than Earth's atmosphere, and composed primarily of nitrogen, creating an environment remarkably similar to what scientists think early Earth might have been like. Titan's surface temperature is about -290 degrees Fahrenheit, cold enough that water ice is as hard as rock, and methane behaves the way water does on Earth, forming clouds, rain, rivers, and lakes. Cassini spacecraft discovered extensive lake systems near Titan's poles, the only stable bodies of surface liquid known anywhere in the solar system besides Earth. Lakes aren't water, they're liquid methane and ethane, hydrocarbons that remain liquid at Titan's frigid temperatures. Moon has a complete hydrological cycle, with methane evaporating from lakes, forming clouds, producing rain, and flowing back through river systems. Combination of organic chemistry, liquid medium, and energy sources makes Titan one of the most promising places to search for extraterrestrial life, though any life there would be utterly unlike Earth life, adapted to a solvent of liquid methane rather than water. Thick atmosphere obscures the surface in visible light, but radar imaging revealed landscapes featuring river valleys, sand dunes, and mountains alongside the hydrocarbon lakes. Europa, one of Jupiter's moons, likely harbours a global ocean beneath its icy surface, kept liquid by tidal heating from Jupiter's gravity flexing the moon's interior. Surface is covered in water ice that's been heavily fractured and refrozen, showing evidence of geological activity. Some regions show chaos terrain where the surface appears to have broken up and reformed, possibly from liquid water erupting from below. Ocean beneath is estimated to be about 60 miles deep, containing more than twice as much water as all of Earth's oceans combined. Such an ocean makes Europa another prime candidate for extraterrestrial life, particularly at hydrothermal vents on the ocean floor, where heat and chemical energy might support ecosystems similar to those found near Earth's deep-sea vents. Ice shell insulating the ocean is probably between 10 and 15 miles thick, though in some regions it might be much thinner. Future missions to Europa will attempt to confirm the ocean's existence definitively, and perhaps even sample material from it, either through landing on the surface or flying through plumes of water that may occasionally erupt into space. Presence of liquid water, chemical energy, and organic molecules makes Europa one of the most scientifically compelling destinations in the solar system. Mars once had liquid water flowing on its surface, with evidence including ancient river valleys, lake beds, and even possible shorelines of a northern ocean. Planet's current atmosphere is far too thin to support stable liquid water, but billions of years ago, Mars had a thicker atmosphere that created a greenhouse effect, warming the planet enough for liquid water to exist. That atmosphere gradually escaped into space because Mars lacks a strong magnetic field to protect it from the solar wind. Earth's magnetic field, generated by convection in its liquid iron outer core, deflects charged particles from the Sun and prevents them from stripping away our atmosphere. Mars once had a magnetic field, evident from magnetized rocks in its ancient crust, but the field shut off when the planet's core cooled and solidified, leaving the atmosphere vulnerable. Water vapor in the atmosphere was broken apart by ultraviolet light, with the light hydrogen escaping to space, while oxygen either escaped or reacted with surface rocks, creating the red iron oxide that gives Mars its distinctive color. Some water remains on Mars today, frozen in polar ice, caps, and probably locked-in subsurface ice deposits. But the planet's surface is now cold and dry, inhospitable to life as we know it. Venus is Earth's closest planetary neighbour and similar in size, yet its surface is hellish, with temperatures around 900 degrees Fahrenheit and atmospheric pressure 90 times that of Earth's surface, equivalent to being 3,000 feet underwater in Earth's oceans. Atmosphere is almost entirely carbon dioxide, with clouds of sulfuric acid, creating a runaway greenhouse effect that makes Venus the hottest planet in the solar system, despite being farther from the Sun than Mercury. Venus probably started with as much water as Earth, but being slightly closer to the Sun meant its surface was warmer, causing more water to evaporate. Water vapor is a greenhouse gas, so it created a feedback loop. More water in the atmosphere trapped more heat, causing more evaporation, until the oceans boiled away completely. Once in the atmosphere, ultraviolet light split water molecules, and the hydrogen escaped to space, while oxygen reacted with surface rocks. Without water, plate tectonics couldn't operate, so carbon dioxide from volcanic activity accumulated in the atmosphere, with no way to be removed through weathering and carbonate formation the way it is on Earth. Venus demonstrates how sensitive planetary climates can be, and how a planet similar to Earth can evolve into something completely different. Mercury, despite being the closest planet to the Sun, has ice in permanently shadowed craters at its poles. Craters never receive sunlight, remaining in perpetual darkness and extreme cold, even though nearby sunlit regions reach temperatures above 800 degrees Fahrenheit. Ice was delivered by comets, small icy bodies that occasionally impact the surface. When a comet impacts in or near a shadowed crater, some of the ice remains frozen because the temperature never rises high enough to vaporize it. Mercury's orbit is unusual, rotating 3 times for every 2 orbits around the Sun, a condition called a 3-to-2 spin-orbit resonance. Pattern resulted from tidal forces from the Sun acting on Mercury's slightly elongated shape. Planet's large iron core, making up about 60% of its mass compared to Earth's 30%, might be the result of a giant impact early in solar system history that stripped away much of the rocky mantle. Mercury's surface resembles the Moon's, heavily cratered and ancient, showing little sign of geological activity in the past few billion years. Extreme temperature variations on the planet, from hot enough to melt, led in sunlight, to cold enough to preserve ice in shadow, demonstrate the importance of atmosphere in moderating climate. Voyager 1 and Voyager 2, launched in 1977, are the most distant human-made objects in existence, now travelling through interstellar space beyond the influence of the Sun. Voyager 1 crossed into interstellar space in August 2012, becoming the first spacecraft to leave the heliosphere, the protective bubble of charged particles and magnetic fields that the Sun creates around the solar system. Voyager 2 followed in November 2018, taking a slightly different path. Both spacecraft continue to send back data about the environment between stars, revealing that interstellar space contains a thin soup of atoms, about 1 atom per 10 cubic centimeters, along with cosmic rays and magnetic fields from other stars. Journey of the Voyagers demonstrates the vastness of even our local neighborhood. Despite traveling at about 35,000 miles per hour for over 4 decades, Voyager 1 is only about 14 billion miles from Earth, barely 1/6 of a light day away. At their current speeds, it would take the voyagers about 70,000 years to reach the nearest star system, if they were headed in that direction, which they're not. Both spacecraft carry golden records with sounds and images from Earth, messages in a bottle for any civilization that might encounter them billions of years from now. Spacecraft like them will outlast humanity, drifting through the galaxy long after our sun has exhausted its fuel and the solar system has changed beyond recognition. Interstellar space isn't truly empty, but filled with an extremely diffuse medium of gas and dust called the interstellar medium, which makes up about 10 to 15% of the visible matter in the Milky Way. Most of it is hydrogen, about 70% by mass, with helium making up most of the rest, and trace amounts of heavier elements. Density is extraordinarily low, typically less than 1 atom per cubic centimetre, compared to about 30 billion atoms per cubic centimetre in Earth's atmosphere at sea level. Despite such extreme thinness, the sheer volume of interstellar space means the total mass is substantial, enough to form hundreds of billions of new stars if it were all to collapse and ignite fusion. Interstellar medium isn't uniform, but exists in different phases depending on temperature and density. Cold molecular clouds, where temperatures drop to just 10 degrees above absolute zero, are where new stars form. Warm neutral regions fill most of the volume. Hot ionized regions, heated to millions of degrees by supernova explosions and stellar winds, create bubbles of extremely thin but energetic gas. Dust grains mixed throughout, each only a few microns across, absorb and scatter starlight, making distant stars appear dimmer and redder than they actually are. Medium like it connects all the stars in the galaxy, recycling matter through cycles of birth and death that have continued for billions of years. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light, constantly bombarding Earth from all directions. Despite the name, they're not rays at all, but actual particles, primarily atomic nuclei stripped of their electrons. Most come from within our galaxy, probably accelerated by the shockwaves from supernova explosions. Supernova remnants act like enormous particle accelerators, using magnetic fields to bounce particles back and forth across the expanding shell of debris, speeding them up with each pass until they reach relativistic speeds. Some cosmic rays carry incredible amounts of energy, with the highest energy particles packing as much energy as a baseball thrown by a major league pitcher, all concentrated in a single atomic nucleus. When cosmic rays strike Earth's atmosphere, they collide with air molecules, creating cascades of secondary particles that shower down to the surface. Fortunately, the atmosphere and Earth's magnetic field shield us from most cosmic radiation, though astronauts in space receive much higher doses. Cosmic rays pose one of the major challenges for human space exploration. Beyond Earth's protective bubble, particles, like them, carry information about the most violent events in the galaxy, though disentangling their origins remains difficult because magnetic fields bend their paths as they travel. Dark matter makes up about 27% of the universe's total mass energy content, yet it doesn't emit, absorb, or reflect light, making it completely invisible except through its gravitational effects. Evidence for its existence comes from multiple sources. Galaxies rotate faster than they should, based on their visible matter alone, suggesting additional unseen mass. Galaxy clusters contain more gravitational mass than can be accounted for by stars and gas. Gravitational lensing, where light from distant objects bends around massive foreground objects, reveals more mass than we can see. Computer simulations of galaxy formation only match observations when dark matter is included. Yet despite decades of searching, no one knows what dark matter actually is. It's not regular matter made of protons, neutrons, and electrons, because if it were, we'd see it interacting with light. Leading candidates include exotic particles that barely interact with ordinary matter, except through gravity, or possibly primordial black holes formed in the early universe, though each possibility has problems. Experiments around the world search for dark matter by looking for the extremely rare occasions when a dark matter particle might interact with ordinary matter. But so far, none have found definitive evidence. Whatever it turns out to be, dark matter shaped the structure of the universe, providing the gravitational scaffolding around which galaxies and galaxy clusters formed. Largest structures in the universe are gravitationally bound superclusters and the vast filaments connecting them, spanning hundreds of millions of light years. Our Milky Way belongs to the local group, which includes Andromeda and about 50 smaller galaxies. Local group is part of the Virgo supercluster, which contains at least 100 galaxy groups and clusters spanning about 110 million light-years. Recent mapping revealed that the Virgo supercluster is actually a small part of an even larger structure called Laniakea, which contains about 100,000 galaxies and spans 520 million light-years. Everything within Laniakea is slowly flowing toward a region called the Great Attractor, a gravitational anomaly that's pulling galaxies in a vast volume of space toward itself. Beyond Laniakea, the cosmic web continues, with filaments connecting superclusters and vast voids separating them. Largest known structures include the Hercules Corona Borealis Great Wall, a galactic filament about 10 billion light-years long, and the Boötes Void, an enormous empty region about 330 million light-years across that contains very few galaxies. Structures like these approach the scale where the universe begins to look uniform, where local variations smooth out into cosmic homogeneity. Existence of structures at such immense scales tells us about the initial conditions of the universe and how gravity sculpted matter over billions of years. Space itself has properties that affect how it can be measured and observed, including something called the Planck length, approximately 1.6 times 10 to the negative 35 meters, which may represent the smallest meaningful distance in the universe. Below such a scale, quantum effects of gravity become so strong that the usual notions of space and time break down. Similarly, the Planck time, about 5.4 times 10 to the negative 44 seconds, might represent the smallest meaningful interval of time. Concepts like these emerge from combining the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When you calculate what happens at distances or times smaller than the Planck scales, the equations predict that quantum fluctuations in spacetime itself become violent and chaotic, with virtual black holes forming and evaporating, and the smooth fabric of space dissolving into something we don't yet understand. Current theories of physics can't accurately describe what happens at Planck scales, which is one reason physicists seek a theory of quantum gravity that would unite general relativity with quantum mechanics. Scales like them represent the frontier of theoretical physics, where the two most successful theories we have, one describing gravity and one describing quantum mechanics, give contradictory predictions. Quantum mechanics governs the behavior of matter and energy at atomic and subatomic scales, revealing that particles don't have definite properties until they're measured. A particle can exist in a superposition of multiple states simultaneously, only collapsing into a specific state when observed. Electrons in atoms don't orbit the nucleus like planets around a star, instead existing as probability clouds that describe where they're likely to be found. Particles can also be entangled, where measuring one instantly affects the other, regardless of the distance between them, a phenomenon Einstein called spooky action at a distance. Quantum tunneling allows particles to pass through barriers that classical physics says they shouldn't be able to cross, essential for nuclear fusion in stars and critical to many modern technologies. Virtual particles constantly pop in and out of existence, even in empty space, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. Empty space isn't empty at all, but seethes with quantum activity. Mechanics like these seem bizarre and counterintuitive, because we evolved to perceive and understand the macroscopic world, where quantum effects average out and become unnoticeable. Particle accelerators, like the Large Hadron Collider near Geneva, Switzerland, smash particles together at nearly the speed of light to recreate conditions similar to those that existed fractions of a second after the Big Bang. By colliding protons at tremendous energies, physicists can create particles that don't normally exist in nature, allowing them to study the fundamental building blocks of matter and the forces that govern them. Discovery of the Higgs boson in 2012 confirmed the final piece of the standard model of particle physics, explaining how particles acquire mass through their interaction with the Higgs field that permeates all of space. Yet, the standard model leaves many questions unanswered. It doesn't explain dark matter or dark energy, doesn't include gravity, and doesn't explain why there's more matter than antimatter in the universe. When matter and antimatter meet, they annihilate in a burst of energy. In the early universe, matter and antimatter should have been created in equal amounts and should have completely annihilated each other, leaving only energy behind. Yet obviously, some matter survived to form everything we see. Some tiny asymmetry must have favored matter over antimatter, but we don't know what caused it. Experiments continue searching for physics beyond the standard model, hoping to glimpse new particles or forces that might answer some of the universe's deepest mysteries. Neutrinos are ghost-like particles that barely interact with ordinary matter, allowing them to pass through entire planets as if they weren't there. Trillions of neutrinos from the sun pass through your body every second without you noticing, because the probability of any single neutrino interacting with your atoms is extraordinarily small. They're produced in nuclear reactions, particularly in the cores of stars and in supernova explosions, and carry information about processes that occur in places we can't see with light. Detection requires enormous tanks of ultra-pure water or other materials buried deep underground to shield them from cosmic rays. When a neutrino occasionally does interact with an atom in the detector, it produces a flash of light that sensitive instruments can record. Neutrinos were once thought to be massless, but experiments in the late 1990s proved they have a tiny but non-zero mass, a discovery that required modifying the standard model of particle physics. They come in 3 types, or flavors, and can transform from one flavor to another as they travel, a quantum phenomenon called neutrino oscillation. Particles like them provide a way to study the universe that's completely independent of light, opening a neutrino astronomy window on cosmic phenomena. Observable universe contains an estimated 2 trillion galaxies, though the exact number is uncertain and may be even higher. Early estimates from the Hubble Deep Field images suggested around 200 billion galaxies, but newer observations and analysis pushed the number higher as fainter and more distant galaxies were detected. Each of those galaxies contains anywhere from a few million to several trillion stars, meaning the total number of stars in the observable universe is roughly equivalent to all the grains of sand on all the beaches on Earth, around 10 to the 24th power, though such analogies barely capture the immensity. Number is so large that if you counted 1 star per second, it would take you longer than the current age of the universe to count them all. And you'd need to continue counting for trillions of times the current age of the universe to finish. Yet, even with so many stars and galaxies, most of the universe is empty space. If you could somehow remove all the matter and energy, the structure that remains, the curvature of space-time itself, would still contain the vast majority of what we think of as the universe. Scale like it can feel overwhelming, making human concerns seem infinitesimal. Yet, it also connects us to something far larger than ourselves, a cosmos that made us possible. Habitable zone around a star is the region where conditions might allow liquid water to exist on a planet's surface, though many factors beyond just distance from the star affect whether a planet can actually support life. For stars like our Sun, the habitable zone extends from about 93 million miles to about 140 million miles. More massive, hotter stars have habitable zones farther out, while smaller, cooler stars have zones closer in. But a planet in the habitable zone isn't necessarily habitable. Venus sits near the inner edge of our Sun's habitable zone, but has a runaway greenhouse effect that makes its surface hot enough to melt lead. Mars sits near the outer edge, but lost most of its atmosphere and is now frozen and dry. Factors that matter include atmospheric composition, magnetic field strength, plate tectonics, the presence of a large moon, distance from disruptive massive planets, and probably many others we haven't yet identified. Astronomers have discovered thousands of exoplanets, planets orbiting other stars, and many of them sit in their star's habitable zone. But whether any of them actually host life remains unknown. Discovering life elsewhere, even simple microbial life, would be one of the most profound findings in human history, answering whether Earth is unique or whether life is common throughout the cosmos. Universe might be just one of many in a vast multiverse, though this idea remains highly speculative and may never be testable through observation. Some versions of quantum mechanics suggest that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. In some versions of inflationary cosmology, our Big Bang might be just one bubble in an eternally inflating space, where new bubble universes constantly form. String theory, which attempts to unify all forces and particles, predicts an enormous landscape of possible universes, with different physical laws and constants. If true, it would mean that the properties of our universe, like the strength of gravity or the mass of the electron, aren't fundamental but random, different in other universes. We can only exist in a universe with properties compatible with the formation of stars, planets, and ultimately life, which might explain why our universe seems fine-tuned for existence. But multiverse theories face a significant problem. If other universes are completely disconnected from ours, how could we ever gather evidence for them? Without testability, some argue these ideas aren't science, but philosophy. Regardless of whether the multiverse exists, we inhabit a universe vast and ancient, enough to inspire wonder, one that operates by comprehensible laws, yet still holds mysteries that may take centuries or longer to unravel. Speed at which the universe expands varies depending on the distance you're measuring, with nearby space expanding slowly and distant. Space expanding faster, a relationship described by the Hubble constant. Current measurements suggest that for every 3.3 million light-years of distance, the recession velocity increases by about 46 miles per second. So, a galaxy 3.3 million light-years away recedes at 46 miles per second. One at 6.6 million light-years recedes at 92 miles per second, and so on. Measuring the Hubble constant precisely has proven surprisingly difficult, with different methods giving slightly different answers. Observations of the cosmic microwave background suggest one value, while measurements using supernovae and other distance indicators suggest a slightly higher value. Discrepancy, called the Hubble tension, might indicate we're missing something important about how the universe works, or it might simply reflect systematic errors in one or both measurement methods. Resolving such a tension is one of the major goals of modern cosmology. Rate of expansion affects the age of the universe we calculate, how far we can see, and ultimately the fate of everything that exists. Understanding expansion helps us reconstruct the history of the universe and predict its future, connecting the distant past to the unimaginably far future. Cosmic microwave background radiation has a temperature of about 2.7 degrees above absolute zero, filling all of space uniformly in every direction. Temperature has cooled dramatically since the early universe, when the radiation was released at about 3,000 degrees. Cooling happened because the expansion of space stretches the wavelengths of photons traveling through it, shifting them toward lower energies and longer wavelengths. Originally released as visible and infrared light, the cosmic microwave background has been stretched into microwave wavelengths over billions of years. Tiny variations in temperature, about 1 part in 100,000, appear as slightly warmer and cooler spots across the sky. Variations represent the seeds of all cosmic structure, regions of slightly higher and lower density in the early universe that eventually grew into galaxies and galaxy clusters. Maps of the cosmic microwave background show these patterns in exquisite detail, revealing information about the universe's geometry, composition, and early evolution. Patterns are slightly polarized, meaning the light waves oscillate in preferred directions, providing additional clues about what happened in the first fraction of a second after the Big Bang. studying radiation like it allows cosmologists to test theories about the universe's origin and evolution with remarkable precision, turning cosmology into an empirical science. Inflation theory proposes that the universe underwent a brief period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, growing from smaller than an atom to perhaps the size of a grapefruit in about 10 to the negative 35 seconds. During inflation, space expanded faster than the speed of light, though this doesn't violate relativity because space itself was expanding, not matter moving through space. Rapid expansion would solve several puzzles about the observed universe, including why it appears so uniform in all directions, despite regions that should never have had time to interact, and why space appears geometrically flat despite the tendency of matter and energy to curve it. Inflation would also explain the origin of the tiny density variations visible in the cosmic microwave background, quantum fluctuations stretched to cosmic scales by the rapid expansion. When inflation ended, the energy driving it converted into ordinary matter and radiation, reheating the universe and beginning the more familiar era of standard expansion. Multiple versions of inflation theory exist, and while the basic idea seems to work well, details remain uncertain, and the ultimate cause of inflation remains mysterious. If true, inflation would mean that everything we can observe, all the galaxies and space between them, originated from a region far smaller than a single atom. Redshift describes how light from distant galaxies is stretched to longer wavelengths as it travels through expanding space, similar to how the pitch of a siren changes as it moves away from you. Astronomers measure redshift by comparing the wavelengths of specific spectral lines, patterns created when atoms absorb or emit light at characteristic frequencies, to their known laboratory wavelengths. A galaxy with a redshift of 1 has had its light stretched to double its original wavelength, meaning wavelengths that were originally in the ultraviolet appear in the visible. Visible wavelengths shift into the infrared, and so on. Higher redshifts indicate greater distances and faster recession velocities. Most distant galaxy observed has a redshift of about 13, meaning we see it as it appeared just 300 million years after the Big Bang. Light from that galaxy has been traveling toward us for over 13 billion years, and during that journey, the universe expanded significantly, stretching the wavelengths. Redshift also tells us about the universe's expansion history, how fast it was expanding at different times in the past. Measuring redshifts of thousands of galaxies allows astronomers to map the three-dimensional structure of the universe and trace how it evolved over cosmic time. Photons, the particles of light, have no mass and always travel at the speed of light in vacuum, making them unique among particles. Because they travel at light speed, photons don't experience time from their own perspective. If a photon could be conscious, it would be emitted and absorbed in the same instant, no matter how far it traveled. Photons carry energy and momentum despite having no mass, and that energy depends on their wavelength, with shorter wavelengths carrying more energy than longer ones. Gamma rays are high-energy photons, while radio waves are low-energy photons, all part of the same electromagnetic spectrum, all traveling at the same speed, but carrying different amounts of energy. When photons travel through space, gravitational fields can bend their paths, an effect called gravitational lensing. Massive galaxy clusters can act like enormous lenses, bending light from more distant galaxies, and sometimes creating multiple images of the same object. Photons can also be absorbed by matter, transferring their energy to atoms and molecules, or they can be emitted when atoms transition between energy states. Every photon that enters your eye, whether from the sun, a distant star, or the glow of the cosmic microwave background, has been traveling through space until the moment it strikes your retina. Spectra of stars reveal their composition, temperature, and motion through characteristic patterns of absorption and emission lines. When light from a star's hot surface passes through its cooler outer layers, atoms in those layers absorb specific wavelengths, creating dark lines in the spectrum. Each element produces a unique pattern of lines, like a fingerprint, allowing astronomers to identify what elements are present and in what proportions. Hydrogen produces a simple series of lines, helium a more complex pattern, and heavier elements create hundreds or thousands of lines. Temperature affects which lines appear and how strong they are, because temperature determines which energy states atoms occupy. By analysing the spectrum in detail, astronomers can determine not just composition, but also surface temperature, pressure, rotation rate, magnetic field strength, and whether the star is moving toward or away from us. If a star has a companion, its spectral lines will shift back and forth periodically as the two orbit their common centre of mass, revealing the presence of the companion, even if it's too faint to see directly. Spectroscopy transformed astronomy from a science that could only measure positions and brightnesses into one that could determine the physical properties and compositions of distant objects. Binary star systems, where two stars orbit their common centre of mass, are extremely common, perhaps more common than single stars like our Sun. Some binaries are so close that their outer layers nearly touch, transferring material between them. Others orbit at vast distances, taking thousands of years to complete one orbit. When a massive star in a close binary explodes as a supernova, it can kick its companion to extremely high velocity, creating what astronomers call a runaway star. Some massive stars are born in triples or even larger groups, creating complex orbital dynamics. In some cases, a white dwarf in a binary system pulls material from its companion, accumulating mass on its surface. If accumulation is steady, it can lead to repeated nova outbursts. If the white dwarf gains enough mass to exceed the Chandrasekhar limit, it collapses and triggers a type Ia supernova, completely destroying the white dwarf. Binary systems with a neutron star or black hole as one component can become powerful X-ray sources as matter spiraling into the compact object heats to millions of degrees and emits high-energy radiation. Studying systems like them teaches us about stellar evolution in environments very different from isolated stars, where interactions between companions can dramatically alter their life cycles. Cepheid variable stars pulsate with regular periods, brightening and dimming in cycles that last from days to months. And the period of pulsation is directly related to the star's intrinsic brightness. More luminous Cepheids pulsate more slowly than less luminous ones. Relationship, discovered by Henrietta Swan Leavitt in the early 1900s, allows astronomers to use Cepheids as standard candles for measuring cosmic distances. By measuring the pulsation period, you know the star's true luminosity. By measuring its apparent brightness as seen from Earth, you can calculate how far away it must be, to appear that faint. Cepheids are bright enough to be seen in nearby galaxies, which is how Edwin Hubble proved that spiral nebulae were actually distant galaxies and not clouds within the Milky Way. Pulsation occurs because the star's outer layers expand and contract, driven by instability in the zone where helium is being ionized and recombined. As the layers expand, they cool and become more transparent, allowing more radiation to escape, which causes them to contract again, creating a self-sustaining cycle. Discovery of the period luminosity relationship gave astronomers their first reliable method for measuring distances beyond the Milky Way, opening up the universe to exploration. Stars form from clouds of gas and dust called molecular clouds, some of which are hundreds of light years across and contain enough material to form millions of stars. Cold and dense regions within these clouds begin to collapse under their own gravity, fragmenting into smaller clumps that become individual stars or star systems. Collapse takes roughly 1 million years for a star like the Sun, much faster for more massive stars. As the cloud contracts, it heats up, eventually becoming hot enough at the center to start fusion. Meanwhile, conservation of angular momentum causes the collapsing cloud to spin faster and flatten into a disk, where planets eventually form. Young stars are often surrounded by disks of leftover material, and observations reveal planets forming within these disks, directly confirming theories of planet formation. Newborn stars go through a phase of violent activity, producing powerful stellar winds and jets that blast material back into space. Eventually, the star settles down into a stable main sequence phase, where it will spend most of its lifetime steadily fusing hydrogen into helium. Process plays out in star-forming regions throughout the galaxy, with thousands of new stars being born each year, continuing the cycle that has created every star we see in the sky. Stellar nurseries like the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, contain hundreds of young stars, less than 1 million years old, along with clouds of glowing gas and dark patches of dense dust, where new stars are currently forming. Nebula glows because ultraviolet light from the hottest young stars ionizes the surrounding hydrogen gas, causing it to emit visible light. Observations in infrared wavelengths reveal even younger stars still embedded in their natal cocoons of dust, invisible in visible light, but glowing brightly in infrared. Some regions show spectacular outflows, where jets of material shoot from newborn stars at hundreds of miles per second, creating shockwaves as they collide with the surrounding gas. Gravity continues to pull material together, so star formation is an ongoing process that will continue in regions like Orion for several million more years. Eventually, the massive stars will explode as supernova, disrupting the remaining gas clouds and perhaps triggering new waves of star formation in neighboring regions, while also injecting heavy elements into the interstellar medium. Regions like them offer astronomers laboratories for studying star formation in action, revealing details impossible to observe in older, more settled stellar populations. Open star clusters are loose collections of hundreds to thousands of stars born from the same molecular cloud, still traveling together through space, though gradually dispersing over hundreds of millions of years. Pleiades, visible as a small group of bright stars in the constellation Taurus, is a young open cluster about 100 million years old, still surrounded by faint wisps of the dust cloud from which it formed. Stars in a cluster have the same age and initial composition, making them valuable for testing theories of stellar evolution. By comparing stars of different masses within a cluster, astronomers can trace how stars of various sizes evolve. More massive stars evolve faster, so in an old cluster, the most massive stars have already died, leaving behind mainly low-mass stars that will live for billions more years. Globular clusters, by contrast, are ancient spherical collections of hundreds of thousands of stars, tightly packed in a region only tens of light years across. They orbit in the halo around the Milky Way, formed when the galaxy itself was young, and they contain some of the oldest stars known. Clusters like them preserve records of stellar populations from different epochs in galactic history, from the ancient globular clusters to young open clusters still forming today. Metallicity, the fraction of elements heavier than helium in a star, affects its properties and evolution in subtle but important ways. Metal-rich stars are slightly cooler at the surface and slightly more opaque than metal-poor stars of the same mass, because heavy elements are more effective at absorbing radiation. Opacity affects how energy flows from the core to the surface, which in turn affects the star's radius and temperature. Metallicity also influences stellar winds, with metal-rich stars losing mass more efficiently through their winds, because metals provide more surfaces for photons to push against. For the most massive stars, metallicity strongly affects their evolution and final fate, with metal-poor massive stars potentially becoming black holes more easily than metal-rich ones. When studying populations of stars, astronomers can identify different generations by their metallicity. Oldest stars in the galaxy are metal-poor because they formed before many generations of enrichment had occurred. Younger stars tend to be metal-rich, formed from material recycled through previous generations of stars. Tracking metallicity across different stellar populations reveals the chemical evolution of the galaxy, showing how the abundance of heavy elements has gradually increased over billions of years. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion, occupying a middle ground between stars and planets. They form like stars, collapsing from gas clouds, but contain less than about 8% the mass of the Sun, not enough for core temperatures to reach the millions of degrees needed for hydrogen fusion. Some confuse deuterium, a heavier isotope of hydrogen that ignites at lower temperatures, but this fuel is quickly exhausted. Without fusion to counteract gravitational contraction, brown dwarfs slowly cool and dim over time, starting at surface temperatures of several thousand degrees and cooling to temperatures comparable to planets over billions of years. Coolest brown dwarfs have temperatures around room temperature, with atmospheres containing water vapor and possibly even clouds of water droplets. Spectroscopy reveals methane in the atmospheres of many brown dwarfs, similar to the giant planets in our solar system. Distinguishing between the most massive planets and the least massive brown dwarfs can be difficult, and the boundary between them may be somewhat arbitrary. Objects like them help us understand the full range of outcomes from star formation and blur the traditional distinction between stars and planets. Exoplanets, planets orbiting stars other than our Sun, number in the thousands confirmed and thousands more awaiting confirmation. First exoplanet orbiting a Sun-like star was discovered in 1995, opening a new era in astronomy. Many early discoveries were hot Jupiters, gas giant planets orbiting extremely close to their stars, completing orbits in just days. Such planets were easiest to detect with early techniques, but probably represent a minority of actual planetary systems. As detection methods improved, astronomers found a remarkable diversity of planetary types, including super-Earths, mini-Neptunes, and systems very different from our own solar system. Some planets orbit binary star systems, experiencing sunrises and sunsets of two suns. Some orbit pulsars, exposed to intense radiation that would likely sterilize their surfaces. Others have extremely elliptical orbits, experiencing wild temperature swings. Most exoplanets have been discovered through the transit method, watching for the slight dimming when a planet passes in front of its star, or through the radial velocity method, measuring the star's wobble caused by the planet's gravitational pull. Diversity of planetary systems discovered suggests that planet formation is robust and common, but also that our own solar system may be somewhat unusual in its architecture. Atmospheres of some exoplanets can be studied using transit spectroscopy, where astronomers analyze starlight that passes through the planet's atmosphere during a transit. As light filters through the atmospheric layers, different gases absorb specific wavelengths, creating a unique signature. Water vapor, carbon dioxide, methane, and other molecules have been detected in exoplanet atmospheres. For the hottest planets, those orbiting very close to their stars, atmospheres contain vaporized metals and silicates, materials that would be solid at Earth's temperature. Some planets show evidence of clouds or hazes that obscure deeper atmospheric layers. Detecting an atmosphere dominated by oxygen, along with other gases like methane, might indicate the presence of life, since oxygen reacts readily with surface materials and would quickly disappear without continuous replenishment. However, abiotic processes can also produce oxygen, so interpretation would require careful analysis of the full atmospheric composition. Next generation of space telescopes will be able to characterize the atmospheres of smaller, potentially habitable planets, searching for biosignatures. Ability to study exoplanet atmospheres transforms the search for life from speculation into an observational science, though conclusive detection of life may remain challenging. Rogue planets drift through space without orbiting any star, possibly ejected from their birth systems through gravitational interactions, or possibly formed in isolation from collapsing gas clouds. Some estimates suggest there might be as many rogue planets as stars in the galaxy, representing a vast population of worlds wandering in darkness. Without a star to warm them, rogue planets would be frozen, their surfaces exposed to the cosmic microwave background radiation at -454 degrees Fahrenheit. However, radioactive decay in their cores and residual heat from formation might maintain subsurface oceans beneath thick ice shells, similar to what's hypothesized for some moons in our solar system. Such oceans could potentially harbor life, though the energy available would be much more limited than on planets orbiting stars. Detecting rogue planets is extremely difficult because they emit no light of their own and reflect no starlight. Occasionally, they can be found through gravitational microlensing, when a rogue planet passes in front of a more distant star and its gravity briefly magnifies the star's light. Population like them represents another possibility for potentially habitable environments, though life on a rogue planet would face enormous challenges compared to life on a star-orbiting world. Tidal forces from nearby massive objects can heat the interiors of planets and moons, through friction caused by repeated stretching and squeezing. Jupiter's moon, Io, experiences such intense tidal heating from Jupiter's enormous gravitational pull that it's the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the moon. Europa, slightly farther from Jupiter, experiences less tidal heating, but enough to maintain a liquid ocean beneath its ice shell. Saturn's moon Enceladus also shows evidence of tidal heating, with geysers of water vapor and ice particles erupting from cracks near its south pole. Tidal heating depends on the strength of tidal forces, which increase with the mass of the primary body and decrease rapidly with distance, and on the eccentricity of the orbit, with more elliptical orbits causing greater variation in tidal forces. Planets in very close orbits around their stars experience tidal forces from the star that can affect their interiors and atmospheres. Over time, tidal forces tend to circularize orbits and tidally lock planets, causing them to always show the same face to their primary. Heating mechanism, like it provides an alternative energy source for maintaining liquid water and driving geological activity on worlds far from the sun's warmth. Asteroid belt between Mars and Jupiter contains millions of rocky objects, ranging from dust-sized particles to Ceres, a dwarf planet about 600 miles in diameter. Total mass of all asteroids combined is only about 4% of the Moon's mass, far less than the mass of a planet. Most asteroids orbit in a relatively flat disk, though some have highly inclined or elliptical orbits. Asteroids are remnants of the planet-forming process, planetesimals that never coalesced into a planet, probably because Jupiter's gravity stirred them to high velocities where collisions became destructive rather than accretive. Composition varies with distance from the Sun, with rocky asteroids dominating the inner belt and more carbon and ice-rich asteroids in the outer regions. Some asteroids are solid chunks of rock or metal, while others are rubble piles, loose collections of fragments held together by their mutual gravity. Occasionally, asteroids collide, creating smaller fragments and fresh surfaces that astronomers can study. Over the solar system's history, gravitational interactions with Jupiter gradually depleted the asteroid belt, ejecting most objects and leaving the sparse population we see today. Objects like them preserve samples of the early solar system's composition, offering clues about conditions during planet formation 4.6 billion years ago. Kuiper belt extends from Neptune's orbit to about 50 astronomical units from the Sun, populated by icy bodies left over from the solar system's formation. Pluto is the most famous Kuiper belt object, large enough to have assumed a roughly spherical shape, but sharing its orbital region with thousands of other objects, rather than dominating gravitationally as true planets do. Many Kuiper belt objects are surprisingly red, probably due to organic compounds called tholins that form when ultraviolet light and cosmic rays bombard ice mixed with methane and other simple molecules. Some have moons, and a few are binary systems where two similar-sized objects orbit their common center. Orbits are often inclined and elliptical, unlike the relatively circular, flat orbits of the planets. Beyond the main Kuiper belt lies the scattered disk, where objects follow even more extreme orbits, probably perturbed by Neptune's gravity during the solar system's early history. Short-period comets, those with orbital periods less than 200 years, originate from the Kuiper belt and scattered disk, their ices sublimating as they approach the Sun and creating the characteristic tails. Region like it extends our solar system far beyond the realm of the planets, containing perhaps more mass than the asteroid belt, but spread over a vastly larger volume. Oort cloud is a hypothetical spherical shell of icy bodies surrounding the solar system at distances from about 2,000 to 100,000 astronomical units, far beyond the Kuiper belt. No object in the Oort cloud has been directly observed because they're too small and too far away to see with current telescopes. But its existence is inferred from the orbits of long-period comets that arrive from all directions rather than from the flat plane where planets orbit. Long-period comets, those with orbital periods of thousands to millions of years, probably originate in the Oort cloud. Occasionally, gravitational perturbations from passing stars or tidal forces from the galaxy nudge an Oort cloud object inward, sending it on a journey toward the inner solar system, where solar heating causes it to develop a coma and tail, becoming a visible comet. Oort cloud might contain trillions of objects with a total mass several times that of Earth, representing the outermost extent of the Sun's gravitational influence. Halfway to the nearest star, it marks the boundary where the Sun's gravity becomes comparable to the gravity of neighboring stars. Region like it reminds us that the solar system's sphere of influence extends far beyond the planets we normally think of, reaching into the space between stars. Comets are icy bodies that develop spectacular tails when they approach the Sun, as solar heating causes their ices to sublimate directly from solid to gas, releasing dust trapped in the ice. Two tails typically form, one of ionized gas pushed away by the solar wind, always pointing directly away from the Sun, and one of dust pushed by radiation pressure, following a curved path. Nucleus of a comet is usually a few miles across, sometimes described as a dirty snowball or icy dirt ball, made of water ice mixed with dust, rocky particles, and frozen gases like carbon monoxide and methane. As it orbits, the comet loses mass with each passage near the Sun, eventually either disintegrating completely or becoming an inactive rocky remnant that no longer produces a coma. Some meteor showers occur when Earth passes through the dusty debris trail left by a comet, with the debris burning up in our atmosphere as shooting stars. Famous comets like Halley's Comet return to the inner solar system at predictable intervals, with Halley's appearing about every 76 years. Short-period comets have been captured into relatively small orbits by gravitational interactions with Jupiter and other giant planets. Objects like them carry relatively pristine samples of material from the early solar system. Their composition altered less than asteroids because they spent most of their history in the cold outer regions. Meteor showers occur when Earth passes through streams of debris left by comets, with dozens of particles per hour entering the atmosphere and creating bright streaks of light. Particles themselves are typically no larger than grains of sand, but they travel at tens of miles per second, and friction with the atmosphere heats them until they vaporize in a flash of light. Most meteors burn up completely at altitudes of 50 to 80 miles, never reaching the ground. Occasionally, a larger object survives the passage through the atmosphere and lands as a meteorite, providing samples of material from asteroids, the Moon, or even Mars, ejected by impacts and eventually captured by Earth's gravity. Meteorites are classified as stony, iron or stony iron, based on their composition, reflecting different formation conditions and parent bodies. Studying them reveals information about the early solar system, including some grains that predate the sun's formation, stardust from previous generations of stars. Isotopic analysis can determine where and when a meteorite formed, sometimes revealing complex histories of heating, melting, and collision. Samples like them offer direct physical evidence about the solar system's history, complementing remote observations of asteroids and comets. Impacts of asteroids or comets with Earth have occurred throughout geological history, with small impacts happening regularly and large impacts rare but potentially catastrophic. Asteroid or comet about 6 miles in diameter struck the Yucatan Peninsula 66 million years ago, creating the Chicxulub crater and likely contributing to the extinction of non-avian dinosaurs, along with about 75% of all species. Impact released energy equivalent to billions of atomic bombs, ejecting enough material into the atmosphere to block sunlight for months or years, disrupting photosynthesis and collapsing food chains. Impacts of such size are rare, happening on average every 100 million years or so. Smaller impacts occur more frequently, with objects a few tens of meters across striking every few thousand years, potentially causing regional devastation. Objects a few meters across enter the atmosphere every few years, usually exploding high in the atmosphere and causing little damage. Astronomers now track near-Earth asteroids, cataloguing objects that might potentially impact Earth in the future. Several asteroids are known that will pass close to Earth in coming decades, though none currently has a significant probability of collision. Monitoring programs aim to provide warning of potential impacts with enough advance time to attempt deflection, turning an inevitable disaster into an avoidable one. Zodiacal light appears as a faint glow along the ecliptic, the path the sun traces through the sky over the course of a year, most visible from dark locations, after sunset or before sunrise. Glow comes from sunlight scattered by dust particles orbiting the sun in the inner solar system, debris from comets and asteroid collisions that slowly spirals inward due to various effects, including radiation pressure and the Poynting-Robertson effect, where photons carry away angular momentum. Dust particles eventually fall into the sun, but the supply is continuously replenished by active comets and occasional asteroid collisions. Gegenschein, or counterglow, appears as a faint bright spot in the sky directly opposite the sun, caused by backscattered light from the same dust cloud. From Earth's orbit, we see the cloud from within, giving us a unique perspective on the dust distribution throughout the inner solar system. Observations from spacecraft beyond Earth's orbit reveal that zodiacal light would appear quite bright from an external viewpoint, making our solar system one of billions, contributing faint scattered light to the cosmos. Phenomenon reminds us that space between planets isn't truly empty, but contains diffuse material that reveals itself through subtle effects like scattered sunlight. Interplanetary space contains the solar wind, a stream of charged particles flowing outward from the sun at speeds of about 300 to 800 miles per second. Solar wind consists mainly of electrons and protons, the components of ionized hydrogen, along with smaller amounts of helium and trace amounts of heavier ions. It originates in the sun's corona, the outermost layer of the solar atmosphere, where temperatures exceed 1,000,000 degrees, and particles have enough energy to escape the sun's gravity. Solar wind is highly variable, with fast and slow streams, and coronal mass ejections can produce sudden bursts of denser, faster material. Earth's magnetosphere deflects most solar wind particles around the planet, but some enter near the poles, creating auroras when they collide with atmospheric gases. Other planets also interact with the solar wind in different ways, depending on whether they have magnetic fields. Mars lacks a global magnetic field, so solar wind interacts directly with its upper atmosphere, gradually stripping it away over billions of years. Stream of particles like it extends far beyond the planets, filling the entire solar system with a tenuous plasma that connects all the planets to our star. Heliopause marks the boundary where the solar wind meets the interstellar medium, about 120 astronomical units from the Sun in the direction the solar system is moving through space. Beyond the heliopause, the Sun's influence on the local environment diminishes, and the properties of space reflect the broader galactic medium rather than solar processes. Voyager 1 crossed the heliopause in 2012, detecting the transition from solar wind particles to the higher density of interstellar material, and noticing changes in the magnetic field and cosmic ray intensity. Transition isn't a sharp edge, but a boundary layer where solar and interstellar plasmas mix. Shape of the heliosphere is probably asymmetric, with a nose in the direction of motion and a long tail streaming behind, similar to the magnetosphere around Earth, but on a vastly larger scale. Other stars produce their own stellar winds and create their own stellar spheres, though we can't observe them directly. Interaction between stellar winds and the interstellar medium creates bow shocks and other structures visible in some stars, particularly fast-moving stars ploughing through denser regions of the interstellar medium. Boundary-like, it defines the realm where the Sun dominates local conditions, beyond which we enter true interstellar space. Local interstellar cloud is the specific region of the interstellar medium through which the solar system is currently passing, a relatively warm and diffuse cloud several light-years across. Properties differ from the broader interstellar medium, with slightly higher density and temperature. Solar system entered the local interstellar cloud a few tens of thousands of years ago, and will remain within it for another few tens of thousands of years before passing into a different region with different properties. Movement through regions with varying density might affect the size and shape of the heliosphere over time, potentially affecting the cosmic ray environment at Earth. Variations in cosmic ray flux might have climate effects, though the mechanisms and magnitudes remain uncertain. Solar system orbits the galactic center, and during that orbit, it passes through spiral arms, interarm regions, molecular clouds, and other environments that expose it to different conditions. Over geological time, changes in the external environment might have influenced Earth's climate, bombardment rate, and possibly even biological evolution, though disentangling these effects from other factors is challenging. Journey through the galaxy exposes the solar system to varying conditions, though the timescales are so long that effects on Earth accumulate slowly. Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend. Bar contains about a third of the galaxy's stars and rotates as a rigid body, unlike the spiral arms. our Sun orbits the galactic center at about 220 million years per orbit, moving at roughly 500,000 miles per hour, yet taking so long to complete one circuit that humans will never live to see the galaxy from a noticeably different angle. Milky Way contains a supermassive black hole at its center, gas and dust lanes, star-forming regions, old stellar populations, and about 200 globular clusters in its halo. Disk is about 100,000 light-years across, but only about 1,000 light-years thick in most places, a flattened structure resulting from angular momentum conservation during the galaxy's formation. Recent observations suggest the disk is slightly warped, probably due to gravitational interactions with satellite galaxies. Galactic rotation isn't uniform, with stars closer to the center, orbiting faster than those farther out, but not following the pattern expected from visible matter alone. One piece of evidence for dark matter. Structure reveals the galaxy's history of formation and evolution over billions of years, shaped by gravity, angular momentum, and mergers with smaller galaxies. Galactic habitable zone is the region within a galaxy where conditions might be favorable for life, balancing factors like the frequency of nearby supernovae, the availability of heavy elements needed for planet formation, and other considerations. Too close to the galactic center, frequent supernova explosions and strong tidal forces might disrupt planetary systems or sterilize planets with radiation. Too far from the center, the abundance of heavy elements decreases, making Earth-like planets less likely to form. Distance alone doesn't determine habitability, since many factors contribute. But statistically, the Sun's orbit about 26,000 light-years from the center might be favorable. Concept remains somewhat speculative, since we don't yet know all the factors that affect the development and persistence of life. Discovery of life on other worlds, or failure to find such life despite extensive searching, might reveal whether a galactic habitable zone is meaningful, or whether life can thrive under a wider range of conditions than currently suspected. Ideas like these guide the search for habitable worlds, though the search remains in its early stages, with much yet to learn. Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way, is about 2.5 million light-years away and contains roughly 1 trillion stars, making it somewhat larger than our galaxy. It's visible to the naked eye as a faint smudge in the constellation Andromeda, and through telescopes it reveals beautiful spiral structure with dust lanes and star-forming regions similar to those in the Milky Way. Observations show that Andromeda is approaching us at about 70 miles per second, and in about 4 billion years, the two galaxies will begin to merge. Merger will take several billion years to complete, with multiple close passes as the two galaxies distort each other through tidal forces before finally settling into a single elliptical galaxy. Stars in Andromeda have similar properties to those in the Milky Way, suggesting that the same physical processes govern star formation and evolution across different galaxies. Like the Milky Way, Andromeda has a supermassive black hole at its center and a retinue of satellite galaxies, and it shows evidence of having absorbed several smaller galaxies in its past. Seeing Andromeda means seeing light that left that galaxy 2.5 million years ago, when our ancestors on Earth were just beginning to diverge from other hominids. Triangulum Galaxy is the third largest member of the local group, smaller than the Milky Way or Andromeda, but still containing about 40 billion stars. Located about 3 million light-years away, it's the most distant object easily visible to the naked eye under dark skies. Its spiral structure is more face-on to our view compared to Andromeda, allowing detailed study of its star-forming regions and spiral arms. Triangulum may be gravitationally bound to Andromeda, possibly orbiting it in a very long period, and it will eventually be involved in the Milky Way-Andromeda merger, adding its mass to the final product. Smaller dwarf galaxies populate the local group, most of them satellites, orbiting either the Milky Way or Andromeda. Dwarf galaxies vary enormously in properties, from the Sagittarius dwarf elliptical galaxy, currently being absorbed by the Milky Way, to ultra-faint dwarfs containing only a few thousand stars, but dominated by dark matter. Local group spans about 10 million light-years, a small corner of the universe, but containing hundreds of billions of stars across dozens of galaxies. Group represents our cosmic neighborhood, the collection of gravitationally bound galaxies that will remain connected even as the universe's expansion carries more distant galaxies beyond the horizon. Elliptical galaxies are smooth, featureless collections of stars with little ongoing star formation, ranging from small dwarf ellipticals to giant ellipticals containing trillions of stars. Unlike spiral galaxies with their flat disks and spiral patterns, ellipticals are three-dimensional, roughly spherical or football-shaped distributions of stars. They contain mainly old red stars, having exhausted most of their gas through previous episodes of star formation. Giant ellipticals often sit at the centers of galaxy clusters, probably formed through mergers of multiple smaller galaxies. Observation shows that most stars in ellipticals follow random orbits, rather than organized rotation like in spiral galaxies, another consequence of their merger origins. Some ellipticals contain small amounts of gas and dust, sometimes showing brief episodes of star formation, and some harbor active galactic nuclei powered by supermassive black holes consuming gas. Merger of two spiral galaxies typically produces an elliptical galaxy, transforming the orderly rotation of the spirals into the random motions characteristic of ellipticals, and using up most of the gas in a final burst of star formation. Galaxies like them represent the end state of galactic evolution in many environments, especially in dense galaxy clusters, where mergers are common. Irregular galaxies lack the organized structure of spirals and ellipticals, appearing chaotic and asymmetric. Some are small galaxies that never developed organized structure, while others are galaxies disrupted by gravitational interactions with neighbors. Large Magellanic Cloud and Small Magellanic Cloud, visible from the southern hemisphere as hazy patches, are irregular galaxies orbiting the Milky Way. Both contain substantial amounts of gas and dust and continue forming stars, with the Large Magellanic Cloud hosting the Tarantula Nebula, one of the largest and most active star-forming regions known. Gravitational interactions with the Milky Way have stripped gas from the Magellanic Clouds, creating a stream of material called the Magellanic Stream that arcs across a large fraction of the sky. Future observations might reveal how common irregular galaxies were in the early universe compared to today, helping to establish how galaxy morphology has evolved over cosmic time. Galaxies like them demonstrate the diversity of galactic forms and remind us that the neat classification into spirals and ellipticals doesn't capture all possibilities. Active galactic nuclei are extremely luminous cores of galaxies, powered by supermassive black holes actively consuming gas, sometimes outshining the entire rest of the galaxy. As gas spirals inward toward the black hole, it heats to millions of degrees and radiates intensely across the electromagnetic spectrum. Jets of material moving at nearly the speed of light shoot out along the black hole's rotation axis, extending for thousands of light years and creating radio emissions. Different types of active galactic nuclei, including quasars, Seyfert galaxies, and radio galaxies, may represent different viewing angles or different stages of the same underlying phenomenon. Quasars, the most luminous type, are most common at high redshifts, meaning they were more common when the universe was younger. Current era has fewer active galactic nuclei, possibly because most supermassive black holes have exhausted the readily available gas in their vicinity. Activity can be triggered by galaxy mergers, which funnel gas toward the central black hole and reignite accretion. Our own galaxy's black hole is relatively quiet now, but may have been active in the past and might become active again in the future. Phenomena like them show supermassive black holes actively shaping their host galaxies through energy and momentum feedback. Quasars are the most luminous persistent sources of electromagnetic radiation in the universe, powered by supermassive black holes consuming gas at tremendous rates. A typical quasar might emit 100 times the light of an entire galaxy containing hundreds of billions of stars, all from a region smaller than our solar system. First quasars were discovered in the 1960s as radio sources that appeared point-like in optical images, hence the name quasi-stellar radio sources. Most are at high redshifts, meaning we see them as they were billions of years ago, when the universe was younger and galaxy collisions were more common, providing fuel for black hole growth. As gas falls toward the black hole, it forms an accretion disk, where friction converts gravitational potential energy into heat and radiation. Inner regions of the disk reach temperatures of millions of degrees, emitting X-rays and ultraviolet light. Radiation pressure can drive powerful winds that blow gas out of the galaxy, potentially shutting off both star formation and further black hole growth in a self-regulating cycle. Objects like them are beacons visible across billions of light years, marking the locations of growing supermassive black holes in the early universe. Gravitational lensing occurs when light from a distant object passes near a massive foreground object, following the curved spacetime around it, and creating distorted, magnified, or multiple images of the background object. Einstein predicted the effect, but the first gravitational lens wasn't discovered until 1979, when astronomers found two quasars very close together in the sky that turned out to be two images of the same quasar, lensed by an intervening galaxy. Strong lensing by galaxy clusters can create spectacular arcs and multiple images of background galaxies. Weak lensing produces subtle distortions in galaxy shapes, measurable only statistically across many galaxies, but useful for mapping the distribution of dark matter. Microlensing by single stars can briefly brighten background stars, or quasars, when the lens passes across the line of sight. Lensing is achromatic, affecting all wavelengths equally, which helps confirm that observed effects are gravitational rather than caused by dust or other wavelength-dependent processes. Lensing magnification allows astronomers to study distant galaxies in more detail than would otherwise be possible, essentially using nature's telescope. to boost observing power. Phenomenon demonstrates general relativity's prediction that mass curves spacetime, turning astronomy into a science that can map invisible mass through its gravitational effects. Cosmic voids are vast regions of space containing few galaxies, typically about 150 million light-years across, separating the filaments and walls where most galaxies are found. Although called voids, they aren't completely empty, containing about 10% of the average density of matter in the universe. Galaxies in voids tend to be smaller and bluer than galaxies in denser regions, reflecting different formation and evolution histories. Voids expand with cosmic expansion, and some models suggest they expand slightly faster than average, contributing to the cosmic web's structure. Formation of voids is a natural consequence of gravitational growth, where slight underdensities in the early universe remained relatively empty as matter flowed toward overdense regions that became filaments and clusters. Shape and size distribution of voids provide cosmological information, constraining models of dark energy and cosmic expansion. Studying voids helps test theories of gravity on cosmic scales, since voids represent regions where matter is sparse and dark. Energy effects might be more apparent. Regions like them make up the majority of the universe's volume, though they contain only a small fraction of its galaxies. Redshift surveys map the three-dimensional distribution of galaxies by measuring their distances through their redshifts, revealing the cosmic web structure of filaments, walls, and voids. Early surveys in the 1980s and 90s covered relatively small areas, but established the basic web-like pattern. Modern surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, creating detailed three-dimensional maps of cosmic structure over billions of light-years. Patterns seen in these maps match predictions from computer simulations based on dark matter and dark energy, providing strong evidence that current cosmological models capture the basic physics of structure formation. Baryon acoustic oscillations, subtle features in the galaxy distribution reflecting sound waves in the early universe, appear as expected in the surveys and provide an independent way to measure cosmic expansion history. Future surveys will map even larger volumes with higher precision, potentially revealing deviations from current models that might point toward new physics. Maps like them transform cosmology into an observational science, allowing direct comparison between theory and measurement across cosmic scales. Sound waves in the early universe, before atoms formed, travelled through the plasma of protons, electrons, and photons, creating oscillations that froze in place when atoms formed and light decoupled. These baryon acoustic oscillations left an imprint on both the cosmic microwave background and on the distribution of matter, creating a characteristic scale about 500 million light-years across in today's universe. That scale appears as a subtle excess in the probability of finding pairs of galaxies separated by that distance, compared to slightly larger or smaller separations. Feature provides a standard ruler for measuring cosmic distances and expansion history, complementing supernovae and other distance indicators. Measuring baryon acoustic oscillations at different redshifts traces how cosmic expansion has changed over time, distinguishing between different models of dark energy. Precision of these measurements has improved dramatically with larger surveys, making them one of the primary tools for constraining cosmological parameters. Imprints from the early universe, like them, connect the present-day structure we observe to processes that occurred when the universe was less than 400,000 years old. Sunyaev-Zeldovich effect occurs when cosmic microwave background photons pass through galaxy clusters and scatter off hot electrons in the cluster gas, slightly increasing the photon's energy. Effect creates a characteristic signature in cosmic microwave background maps: a slight deficit of photons at millimeter wavelengths and slight excess at shorter wavelengths. Unlike most observational techniques that become more difficult with increasing distance, the Sunyaev-Zeldovich effect's strength doesn't diminish with redshift, making it valuable for finding distant galaxy clusters. Combined with X-ray observations and gravitational lensing, it provides multiple independent ways to measure cluster masses. Clusters represent the largest gravitationally bound structures in the universe, and their abundance at different redshifts constrains cosmological models, particularly the properties of dark energy, which affects how quickly structure grows. Small-scale variations in the effect can probe the pressure and velocity structure within cluster gas, revealing how energy from active galactic nuclei and supernova affects the intracluster medium. Effect like it provides another window on the universe's structure, connecting the cosmic microwave background to massive structures that formed billions of years after the background was emitted. Galaxy clusters contain hundreds to thousands of galaxies bound together by gravity, typically spanning several million light-years across. Most of the ordinary matter in a cluster isn't in stars, but in hot gas between galaxies, heated to tens of millions of degrees by gravitational compression as the cluster formed. Gas is so hot that it emits X-rays, making galaxy clusters luminous X-ray sources, even including all the stars and all the gas. Ordinary matter makes up only about 15% of the cluster's total mass, with the remaining 85% being dark matter. Dark matter creates the gravitational potential well that holds the cluster together and shapes the distribution of gas and galaxies. Clusters grow over time as smaller groups of galaxies fall in and merge, and the history of mergers can sometimes be seen as disturbances in the X-ray gas distribution, or as elongated galaxy distributions. Cluster collisions, like the famous bullet cluster, provide some of the clearest evidence for dark matter, since the dark matter appears to pass through largely unaffected, while the gas slams together and heats up. Structures like them represent the largest organized systems in the universe, great cities of galaxies held together by dark matter's gravitational embrace. Intracluster light comes from stars stripped from their galaxies during close encounters or tidal interactions within galaxy clusters, forming a diffuse glow between galaxies. These orphan stars follow the cluster's overall gravitational potential, rather than belonging to any particular galaxy. Measurements suggest that intracluster light can represent 10 to 50% of the total light from a cluster, meaning a significant fraction of stars have been liberated from their home galaxies. Studying intracluster light provides information about cluster assembly history, since more dynamically evolved clusters tend to have more intracluster light. Stars producing such light are difficult to observe individually at the distances of galaxy clusters, but their combined glow can be detected and mapped. Some brightest cluster galaxies, the massive elliptical galaxies typically found at cluster centers, have extremely extended halos that blend into the intracluster light, suggesting these galaxies continue growing by accreting stars from their surroundings. Light like it reveals the violent history of galaxy clusters, where collisions and near misses gradually transfer stars from galaxies to the broader cluster environment. Superclusters are groups of galaxy clusters that appear close together in space, though whether they're gravitationally bound or merely overdense regions depends on their specific properties. Laniakea supercluster, containing our local group and spanning about 500 million light-years, is defined by the pattern of galaxy motions converging toward a common center. Unlike galaxy clusters, most superclusters are probably not gravitationally bound and will gradually disperse as cosmic expansion continues. Some regions contain multiple superclusters arranged in walls or sheets, creating an even larger scale pattern in the galaxy distribution. Great Attractor, a gravitational anomaly toward which the local group and neighboring galaxies are moving, represents a large concentration of mass, possibly a massive cluster or group of clusters partially hidden behind the plane of the Milky Way. Measurements of peculiar velocities, the motions of galaxies relative to the overall cosmic expansion, reveal how mass is distributed on the largest scales and how gravity continues to affect structure even as expansion accelerates. Structures like them represent the upper end of the hierarchy of cosmic organization, where gravity still affects large-scale flows despite the expansion of space. Cosmic strings are hypothetical one-dimensional defects in space-time that might have formed during phase transitions in the very early universe, analogous to cracks that form when water freezes. If they exist, they would be incredibly thin, far thinner than an atomic nucleus, but enormously massive, with a mile-long segment potentially massing more than Earth. A cosmic string moving through space would create gravitational effects, including distinctive lensing signatures, producing double images of background objects aligned along a line rather than the arc or multiple images expected from lensing by a massive object. Despite decades of searching, no cosmic strings have been definitively detected, placing strong limits on their abundance and properties. Some theories of fundamental physics predict cosmic strings, while others don't, so their detection or definitive absence would provide information about physics at energy scales far beyond what particle accelerators can reach. Other types of topological defects, including domain walls and monopoles, are also predicted by some theories, but remain unobserved. Objects like them would represent fossil remnants of the universe's earliest moments, preserved through billions of years of cosmic evolution. Anthropic principle suggests that we observe the universe having properties compatible with our existence, because we couldn't observe a universe incompatible with our existence. Weak form is a tautology. Observers necessarily observe conditions suitable for observers. Strong form suggests that the universe must have properties allowing life to develop, which some interpret as evidence for purpose or design, while others see as selection effect in a multiverse. Many physical constants appear finely tuned, meaning small changes would make the universe inhospitable to life as we know it. If gravity were stronger, stars would burn out quickly. If weaker, stars might not form. If the strong nuclear force were slightly different, carbon might not be stable. However, many parameters could vary together, and we don't know whether these are the only possible ways for complexity to arise. Anthropic reasoning remains controversial, with some physicists seeing it as legitimate reasoning, while others view it as abandoning the search for deeper explanations. Question of whether our universe's properties are inevitable, random, or selected remains open. Principle reminds us that any observers necessarily find themselves in a universe capable of producing observers, though what that implies about reality's deeper nature remains debated. Fine structure constant, approximately 1 divided by 137, describes the strength of electromagnetic interactions and appears in numerous physical formulas. Its value affects atomic structure, chemical bonding, and stellar evolution. If it were significantly different, atoms would have different properties, chemistry would be altered, and stars might not function as they do. No theory currently explains why it has the value it does rather than some other value. Some physicists have asked whether the fine structure constant might vary slowly over cosmic time or differ in different regions of the universe. Most measurements show it to be constant across observable cosmic history and distance, but occasional claims of small variations remain controversial. Constants like it connect fundamental physics to the structure of matter and energy throughout the universe, and understanding why they have their observed values might reveal deep principles about how nature works. String theory suggests that what we call constants might actually be variables that took particular values as our universe evolved, different in other universes if such exist. Constants like them define the character of physical law in our universe, parameters that determine everything from atomic spectra to the lifespan of stars. Vacuum energy, the energy of empty space itself, contributes to cosmic expansion through what we call dark energy. Quantum field theory predicts that even empty space should have energy from virtual particles constantly appearing and disappearing. But straightforward calculations give results about 120 orders of magnitude larger than observed vacuum energy. Such an enormous discrepancy, called the cosmological constant problem, represents one of the biggest unsolved puzzles in physics. If vacuum energy were as large as naive calculations suggest, the universe would have expanded so rapidly that no structures could have formed. Why it has such a small but non-zero value remains mysterious. Some theories propose that vacuum energy might change over time or vary in different regions, while others suggest we're missing something fundamental about how to calculate quantum contributions to vacuum energy. Dark energy's effects only became apparent when the universe was about half its current age, before which matter and radiation dominated cosmic dynamics. Energy like it demonstrates how even empty space has properties that affect the universe's evolution, connecting quantum mechanics to cosmology in ways we don't fully understand. Heat death represents one possible ultimate fate of the universe, where expansion continues forever, stars exhaust their fuel, black holes evaporate, and eventually all energy becomes uniformly distributed as low-grade heat. Process would take incomprehensibly long, far longer than the current age of the universe. Stars will continue forming for perhaps another trillion years, as remaining gas clouds slowly collapse. But eventually, all gas will be locked in stars, planets, or stellar remnants. Stars that exist will eventually burn out, with the longest-lived red dwarfs persisting for trillions of years. Black holes, even supermassive ones, will eventually evaporate through Hawking radiation over timescales of 10 to the 100 years or longer. After black holes evaporate, the universe will contain only isolated particles and radiation in a space expanding exponentially, growing ever more dilute and cold. Some theories propose that protons might decay over extremely long timescales, eventually breaking down even the remnants of stars and planets into radiation. Whether the universe actually follows such a trajectory depends on whether dark energy remains constant or changes over time. Fate, like it seems, bleak from a human perspective, but it represents a valid solution to how the universe's story might end, slowly fading rather than ending catastrophically. Big Rip is an alternative fate where dark energy grows stronger over time, eventually tearing apart all bound structures from galaxy clusters down to atoms. If dark energy's density increases as the universe expands rather than remaining constant, acceleration would strengthen, first separating gravitationally bound structures like galaxy superclusters, then clusters, then galaxies, then star systems. Eventually, atomic nuclei and even atoms themselves would be torn apart as spacetime's expansion overwhelmed all binding forces. Scenario remains speculative and depends on dark energy having properties different from a simple cosmological constant. Current observations slightly favor a constant dark energy density, but uncertainties remain large enough that strengthening dark energy can't be ruled out. Big Rip would occur at a definite future time, determined by dark energy's properties, possibly tens of billions of years from now, or possibly much later. Other scenarios include oscillating universes that undergo repeated cycles of expansion and contraction, or universes that eventually begin contracting in a big crunch, though current evidence suggests expansion will continue indefinitely. Speculation about the ultimate fate reminds us how much depends on properties we're only beginning to measure, and theoretical questions we've barely begun to answer. Observable universe represents only a tiny fraction of what might exist beyond the cosmic horizon, regions so distant that their light hasn't had time to reach us yet. Every calculation suggests that the total universe is vastly larger than the observable part, possibly infinite in extent. If space continues uniformly beyond what we can see, then every possible configuration of matter must occur infinitely many times, meaning infinite copies of you, me, and everything we've ever known exist somewhere in that vastness. This follows from probability. With infinite space and only finitely many ways to arrange matter in any given volume, arrangements must eventually repeat. Whether such distant regions really exist, and whether they're meaningful, if they can never be observed, remains philosophical rather than scientific. What we can observe, the universe within our cosmic horizon, contains enough wonder to occupy humanity's attention for centuries or millennia to come. 2 trillion galaxies, each containing billions or trillions of stars. Planets orbiting those stars. Matter and energy following comprehensible physical laws, all connected through space and time into a coherent whole. So, wherever you are, allow your mind to rest. Let your breath slow. Let your thoughts grow soft at the edges. The cosmos continues its ancient dance. Galaxies spinning through space. Stars burning their nuclear fuel. Planets tracing their patient orbits. All following the same elegant laws that have guided cosmic evolution for 13.8 billion years. The journey through the universe's wonders doesn't end. It simply pauses here until curiosity calls again. Sleep well, and thank you for exploring the cosmos with us.